So Riemann surfaces, this is really more for interest than something we'll actually use. Basically, there's another way to deal with multi-value functions. As far as I know, it's not terribly useful. Well, it's not really going to be used for the techniques we're going to use complex variables for. But it removes the need for branch cuts. The problem is the shapes and spaces you end up dealing with are much more complicated. Anyway, so what happens? So for a function where it has n possible values, so we're talking about multi-valued functions still, n possible values, we say that there are n complex planes stacked on top of each other, and these planes are called sheets, and each of those sheets corresponds to a different branch of the function. Okay, so how do we get rid of the branch cuts? Well, where we would normally find a branch cut, we connect one sheet to the next one. So if we want to move from n equals 1 branch to n equals 2, where you get a branch cut, those two sheets corresponding to those branches are connected at the branch cut. So when you pass through where the branch cut would be, you're basically just smoothly passing from one sheet to the next. So this set of connected sheets is known as a Riemann surface. The simplest type of Riemann surface is the complex plane itself. That's just one sheet, which just represents the complex number z. The next simplest Riemann surface, or the simplest Riemann surface which for a multi-value function, is actually the one for log z. It's simple in the sense that its structure looks quite simple. It can be represented by a helical surface, as shown here. It contains an infinite number of sheets, obviously, because n, the number of possible values, is infinite. But you can at least stack them, and the branch cuts are simple, and basically leads to a helical structure. It looks like a helical structure. You can think of the branch cuts as sort of being lines along here. When you go round and round, you're effectively meeting where the branch cut would be, and then going up one level. So it's sort of a bit like a car park, multi-story car park. Now, the reason why Riemann surfaces generally can't be viewed properly in three-dimensional space without the surface sort of artificially passing through itself is that the last sheet of the Riemann surface must be connected back to the first sheet. So for example, for the Riemann surface for the square root of z, z to the half, the surface will intersect itself along the usual branch cut, v equals pi. And basically what happens is that as you increase theta from 0 upwards, you sort of go round, and you end up going round twice before you come back and reach your starting point. That's basically because if you imagine putting z equals r e to the I theta, and then raising that all to the power half, when do you get to the same value again? Well, it's not when theta equals 2 pi, because then when you substitute that in, when you raise e to the I 2 pi to the half, then you get e to the I pi, which is minus 1. So you don't get the same thing. You only get the same thing when theta equals 4 pi. Then when you raise that to the half, then you get e to the I 4 pi times 1/2, which is e to the I pi, 2 pi, which is 1, which is back where you've started. Okay, so as I said, these are just sort of for interest. They're not amazingly useful for what we're going to be doing. However, the next concept, which is actually also a very simple Riemann surface, is actually can be quite useful, and that is of the Riemann sphere. And it's another way of thinking of all of the complex numbers. So the one we're more familiar with is the Argand diagram, or the complex plane. But we can actually represent all complex numbers as points on a sphere known as the Riemann sphere. Now, the way I'm going to define the Riemann sphere is a little different from the way most other people define it. I think my way has a slight advantage, as we'll soon see. But what we do is referring to this figure here. So we've got the complex plane here, and to find out what point on, and this is our Riemann sphere. So our Riemann sphere is a sphere of radius 1, and the way I do it is make the equator of this Riemann sphere coincide with mod z equals 1, the unit circle on the complex plane. Then to find out what the complex number A is on the complex plane, what that corresponds to on the Riemann sphere, we simply draw a line from the north pole of the Riemann sphere to the point on the complex plane and look at where it intersects the sphere. And that point A dashed represents the complex number A, but on the Riemann sphere. So that basically means that any complex number which has modulus greater than 1 will end up on the northern hemisphere of this Riemann sphere, and any complex number which has modulus, for example B, which has modulus less than 1, will end up on somewhere in the southern hemisphere of this Riemann sphere. Clearly, the origin and the complex plane then ends up getting mapped to the south pole, and points on the unit circle just get mapped to themselves. Now, what's the point of introducing the Riemann sphere? Well, think what happens as A gets further and further away. The point gets mapped closer and closer to the North Pole. And this is true for A in any direction. If you imagine if A is over here, then it still gets mapped closer and closer to the North Pole. So what are we saying? Well, basically, it means that for any point infinitely far in any direction on the complex plane, so infinitely far away from the origin on the complex plane, it gets mapped to the same point, just to the North Pole, the limit. So we call this North Pole the point at infinity. And strictly, this point at infinity doesn't correspond to any point in the complex plane, because the complex plane doesn't actually include infinity, okay, because infinity is not strictly a number. So the advantage of the Riemann sphere is that it naturally includes this so-called point at infinity, which is not in the complex plane. So we actually sometimes call it the extended complex plane, and denote it by this. So C sub infinity is the set of complex numbers C plus, we put it in a strange notation, well, it's a set which includes the point infinity. And we regard infinity as a single point. This point infinity actually has the meaning that it includes both minus infinity and plus infinity. Both of those, if this is the real axis, would get mapped to the same point. And also any complex number times infinity. So that includes minus I infinity, plus I infinity, or e to the I theta, where theta is anything times infinity. All of these get mapped to the same point. So we regard all of these difficult, I don't really want to call them numbers, but okay, these quantities, minus infinity, infinity, as the same thing, just the point at infinity, which is just represented by the symbol infinity. Well, why is this useful? Well, it means that now we're allowed to write 1 divided by 0 equals infinity, which you can't do if you're dealing with just the real numbers or the complex numbers, since there's no unique value of 1 over z as z goes to 0. Because if you go to 0 along the negative real axis, you'll get minus infinity. If you go to 0 along the positive axis, you'll get plus infinity, and so on. But having this idea of a Riemann sphere, we can now uniquely define 1 over 0 as infinity, because there's only one infinity. Okay, so this does actually have uses a bit later on. It's a useful idea just to have one infinity in certain things.